Hi friends, welcome to learn fundamentals of data structures and algorithms course. In this session, we focus on the performance analysis of an algorithm. In the previous session, we have discussed the space complexity of an algorithm. The space complexity of an algorithm defines how much computational space is required during the execution of an algorithm. In this session, we focus on the computational time complexity of an algorithm. In the performance analysis of an algorithm, we need to focus on the second complexity, time complexity. We will focus on how to find the time complexity of the given algorithm. In this session, we focus on the computational time complexity of an algorithm. The time complexity of an algorithm defines the computational time required to complete the execution of the algorithm. The computational time does not depend on the compile time. In time complexity, we need to consider two things. One is a compile time, second one is a runtime. Compile time does not depend on the problem instance characteristics. Compile time does not depend on the problem instance characteristics, because once the program is compiled, it can be run any number of times. So clearly the time complexity depends on only the runtime of the algorithm. Runtime of the algorithm depends on the problem instance characteristics. Runtime of the algorithm depends on the problem instance characteristics. So we need to find how many number of operations are executed by the algorithm. Total number of operations performed by the algorithm. To find the total number of operations performed by the algorithm, let us define the notation T P of n. T indicates the time complexity. P is the program or algorithm. N defines the problem instance characteristics. For example, n defines the size of the input. If we define a Tp of n, the time complexity of the program or algorithm for the input size n, using this expression, a Tp of n is equal to Ca into add of n plus Cs into sub of n plus Cm into mul of n plus Cd into div of n plus etc. In this expression, let us assume that the constants Ca, Cs, Cm, Cd define the time needed to perform the addition operation, subtraction operation, multiplication operation and division operation, right. Let Ca be the time required to perform the addition operation, Cs defines the time required to find the subtraction operation. Cm defines the time required to find multiplication operation. Cd defines the time required to define the division operation, etc. Let add of n be the number of additions carried out. Add of n, right, as a function which defines the total number of additions carried out in the algorithm. Likewise, sub of n, which defines the number of subtractions performed in the algorithm. Then mul of n, which defines the count on the number of multiplications performed, and div of n, which defines the number of divisions performed, etc. So, if we multiply the time needed to perform the addition operation with the number of multiplications and the time needed to perform the subtraction operation with the number of subtractions and the time needed to perform the multiplication operation with the total number of multiplications and the time needed to perform the division operation with the total number of divisions performed, right, plus etc., we will get the total time needed to complete the execution of the algorithm. In this computational expression, if we write the expression a plus b, the time needed to find a plus b, should be the same for all operands a and b. For example, if we consider a star b, time needed to find a star b is not the same for all operands a and b. That means time needed to find 4 into 5 is not the same as, say, 4000 into 5000. So, the time needed to find the expression 4 into 5 is not equal to the time needed to find the expression 4000 into 5000. So, in this stage the formula computation is not an efficient methodology, right. So, we need to ignore this kind of formula computation to find out the time complexity of the given algorithm. Instead, we need to focus on two important methods. For that, we need to find the count on the total number of operations performed by the algorithm. Count on the total number of operations performed by the algorithm. To find the total number of operations performed by the algorithm, what we have to do, we need to consider, or we need to count only the number of program steps. We need to count only the number of program steps. So, let us define what is a program step. Program step. Program step is syntactically and semantically a meaningful segment of the program. Meaningful segment of the program that has an execution time that is independent of the problem instance characteristics. Program step is syntactically and semantically a meaningful segment of the program that has an execution time that is independent of the problem instance characteristics. So, how to find the program steps count? We need to consider comments. Comments are comments are completely ignored, right, as the program steps. And we need to consider the assignment statements. Assignment statements. In case of simple assignment statements, for example, s is equal to 0, which does not involve a function call, this can be taken as one step per execution. S is equal to 0 or s is equal to s plus a of I. These are simple assignment statements which do not take any function call. So, these are taken as one step per execution. Then in case of control statements, for, while, do while and repeat until, we need to consider only the conditional part of the control statement. We need to find a count on how many times the condition is going to be executed in case of a control statements. So, including the count for each program step, we need to find the total number of operations performed by the algorithm. So, we need to find out the total number of operations or total number of execution steps performed by the algorithm. For that we have two methods. One is a step count method, second one is step table method. Step count and step table methods determine the total number of executable statements, total number of executable steps or statements, instructions in the given algorithm. Let us explore these methods in detail. First one is a step count method. Step count method. In step count method, we need to find the total number of executable statements or instructions in the given algorithm. Step count method introduces a global variable, say count as a global variable. We need to introduce with initial value 0, set count is equal to 0. The global variable count is initialized to 0. Whenever we need, we are finding an executable statement, that means we have a program step instruction, we need to increment the count by 1. Count is equal to count plus 1. For each a program executable step instruction, what we have to do, we need to increment the count variable by 1. That means count is, we need to set count is equal to count plus 1. At the end of the algorithm, we need to find the value of count. So that we can have the total number of executable steps or instructions in the given algorithm. This is the procedure in finding the total number of executable steps using the step count method. Now, let us illustrate the step count method. Example 1, step count method. Step count method to find the array sum. Let us define the algorithm to find the sum of n numbers which are stored in an array. Algorithm sum A array comma n. What is an array A? A is a one dimensional array which consists of n elements. The array elements are referred as A1, A2, A3, etc. An. N represents the size of the array. Let us devise the algorithm to find the sum of the elements, right. That is, we need to find S is equal to A1 plus A2 plus A3 plus etc. An. To find this expression, let us define the initialization S is equal to 0. Then defining the for loop for I is equal to 1 to n do. Then we will write S is equal to S plus A of I for n's here, n for, then finally we need to return a value of S. Return is closing curly brace. This is the end of algorithm sum. In this algorithm, now let us apply the step count method. In step count method, what we have to do, we need to set a global variable count, right. So, introduce a global variable count. The variable count should be initialized to 0. For example, here count is a global variable. Initial value of count is 0. Whenever we find one executable statement, that means whenever we find a program step, that is syntactically or semantically the meaningful segment of a program that has an execution time that is independent of the problem instance characteristics. So, whenever we find a program step, instruction, executable statement, we need to introduce the count. That means we need to increment the count by 1. Now, have a look into the statement S is equal to 0. This is one assignment statement. The assignment statement which does not involve any other function calls. So, this is taken as a single step per execution. So, whenever we find a single step per execution, we need to increment the count by 1. For the execution of S is equal to 0, here for example, after this line, I introduce count is equal to count plus 1. Now, count is incremented by 1. Before the statement S is equal to 0 or after S is equal to 0, we can introduce the corresponding count. Count is equal to count plus 1. Next, in case of for, while, do while control statements, we need to introduce the count only for the conditional part. For example, for right initialization I is equal to 1, last value right I is equal to n, I is equal to 1, termination value is I is equal to n. We will not write include a count right to have this assignment or initial setting I is equal to 1. Instead, we need to check the count right only for the conditional part of the for statement. So, when I is equal to 1, it checks a condition if I is less than or equal to n. For this, we need to introduce the count by 1. When I is equal to 2, we need to check a condition if I less than or equal to n. Count should be included. When I becomes 3, checking if I less than or equal to n, the count should be included. Likewise, when I becomes n, checking if I less than or equal to n, we need to increment the count by 1. When I becomes n plus 1, checking the condition if I less than or equal to n, corresponding count should be included. Count is equal to count plus 1, right, should be executed. So, for I is equal to 1 to n do initialization to be ignored, only the conditional part what is the conditional part? Checking if I less than or equal to n. Only to execute this conditional part, we need to increment the count by 1. So, for I is equal to 1 to n do, even we have a single statement, we need to modify here introducing the braces or here for n for okay. For I is equal to 1 to n do, here I introduce the statement count is equal to count plus 1. This count is equal to count plus 1, this is introduced to check the conditional part. In comment right, I have written here conditional part check I less than or equal to n. Checking the conditional part I less than or equal to n, this is taken as one step per execution, hence associated count is introduced here at the first statement of for count is equal to count plus 1. This count is equal to count plus 1 counts the count for these conditional tests I is equal to 1, I is equal to 2, I is equal to 3, etc. I is equal to n. Because if the condition is true, then only control goes to execute the part of for. When the control comes out of the for, right, that stage, right, what happens? This conditional count, when I becomes n plus 1, checking if n plus 1 is less than or equal to n, this conditional test count is not included in this count statement, because checking if n plus 1 less than or equal to n, condition becomes false. Control comes out of for here when n plus 1 less than or equal to n. Since condition is false, control comes out of the for. So, checking if n plus 1 less than or equal to n is treated as one step per execution actually. So, we need to introduce the count corresponding to this conditional test. So, here after the for, that means after for n for, here we need to introduce one count statement. So, writing here count is equal to count plus 1, in comment right, let us write n plus 1 less than or equal to n question mark. When I becomes n plus 1, right, checking if I is less than or equal to n, that is I is equal to n plus 1 less than or equal to n. For this conditional part, right, count is introduced here after the for. So, just understand, for I is equal to 1 to n do means, right, for loop condition is tested for n plus 1 times. How? When I is equal to 1, I less than or equal to n is tested. When I is equal to 2, 2 less than or equal to n is tested. When I is equal to 3, 3 less than or equal to n is tested. Likewise, when I becomes n, I less than or equal to n is tested. Then finally, when I becomes n plus 1, I less than or equal to n is going to be tested. So, for loop is executed for n plus 1 times. For n times, right, the associated count is introduced in this count statement. Count is equal to count plus 1. When I becomes n plus 1, since condition becomes false, control has to come out of the for loop. The associated count is introduced here. Count is equal to count plus 1. Then inside the for, right, we have the assignment statement s is equal to s plus a of I. This is one executable statement, a simple statement which does not involve any function call. So, to introduce the execution of s is equal to s plus a of I, we need to write one count statement. Count is equal to count plus 1 before this before this assignment statement or after this assignment statement. Then return is a control is going to return the value, right, sum to the calling place. So, before this return statement, here we are introducing the count statement. Count is equal to count plus 1. This is for the return statement, because return is an executable statement. Return, right, some value, values, right, returned to the calling place. Return statement, this is taken as one step per execution. So, to introduce the count for the return statement, we need to introduce, right, before the execution of the return statement, because after the return statement, control will never, right, execute the subsequent statements. So, before this return, s count is equal to count plus 1 is introduced. So, for all the executable instructions or program steps, the count statement is properly introduced. S is equal to 0, right, count is introduced here. For conditional test, right, one time here tested, then when I becomes n plus 1, right, that has been given outside the for n for. S is equal to s plus a of I, right, this is associated with this count statement. Return s is associated with this count statement. So, proper count statements are introduced. Now, we need to find the final value of count, assuming the global variable count is set to 0. Understand? Now, count is set to 0 because count is a global variable. When the algorithm, right, begins execution, we need to find, right, what will be the final value of count. That is important. Initially, right, count is equal to 0. So, it seems that here count is equal to count plus 1. Count is executed, right, count is incremented by 1. Then here after the for, we have introduced twice count is equal to count plus 1, and here, right, count is equal to count plus 1. So, these two statements, right, count is equal to count plus 1, here count is equal to count plus 1 can also be written as count is equal to count plus 2, and including, right, this s is equal to 0, count is equal to count plus 1. These three count statements are, right, not placed as the part of for. So, we can write, right, in a single line simply count is equal to count plus 3. Thrice a count is executed outside the for. Inside the for each value of I, a count is incremented twice. For I is equal to 1, this count is incremented, count is equal to count plus 1. Then s is equal to s plus a of I, after this count is equal to count plus 1 gets executed. So, for each I, the variable count is incremented twice. I ranges from 1 to n, I is equal to 1 to n. For each I, a count is incremented twice. So, since I ranges from 1 to n, so inside the for, right, we have placed the count statements. Count is equal to count plus 1, then s is equal to s plus a of I, after that count is equal to count plus 1. Now, the effect of this count increment inside the for is, right, twice for each I. So, in general, count is equal to count plus 1 inside the for will have the count of 2n times, 2n times inside the for. That means count is incremented 2n times inside the for loop. Outside the for loop, right, 3 times count is incremented outside the for loop. How 3 times? S is equal to 0, count is equal to count plus 1 time. After n for, count is equal to count plus 1. Before return is count is equal to count plus 1. So, thrice, right, a count is incremented outside the for loop. So, adding all these, right, we will have 2n plus 3 times. So, we can write T, the algorithm name is sum array a comma n. So, T sum input size is n, this is equal to 2n plus 3, where n represents the input size. So, what is 2n plus 3? 2n plus 3, which indicates 2n plus 3 steps are the total number of executable steps or instructions in the algorithm sum with input size n is 2n plus 3. This is the interpretation. Since a count is initially 0, once the algorithm completes its execution, the final value of count is clearly 2n plus 3 steps.